there would be hardly any student of statistics who hasn't heard of beta 1 and beta 2 coefficients. Beta 1 and beta 2 coefficients in most of the universities are taught in the first year of the statistics course. Beta 1 coefficient is used to measure skewness, and beta 2 coefficient is used to measure kurtosis in any given data set. These two coefficients are some functions of central moments. Beta 1 is defined as the ratio of the square of the third central moment and the cube of the second central moment. Whereas beta 2 is defined as the ratio of the fourth central moment and the square of the second central moment. Moments, all of us very well know that they measure different characteristics of populations. For example, the first moment gives the mean of a population. It gives the measure of central tendency. The second moment measures the amount of dispersion in a population. The third and the fourth moments indicates respectively skewness and kurtosis in a population. About the fifth and the higher moments are perhaps not known yet as to which characteristics of populations they measure. But this much is certain, that they might be indicating some other finer characteristics of populations. As the main objective of statistics is to study populations, to study different characteristics of populations. Moments are of very vital use in statistics in this respect. Here, there arises one question. Have you ever thought that when only the third central moment mu3 measures skewness, then what is the need of defining a new measure beta 1 and making the measure of skewness complicated? What is the need of using the second central moment mu2 in it? Mu2 doesn't measure skewness. Not only that, what is the logic? What is the rationale behind squaring the third central moment and taking the cube of the second central moment in beta 1? Similarly, when only the fourth central moment mu4 measures kurtosis, then what is the need of defining a new measure beta 2 and making the measure of kurtosis more complicated? What is the rationale behind taking in beta 2 only the first power of the fourth central moment and the second power of the second central moment? I will explain to you why it is done so. It is true that the third central moment is sufficient to measure skewness, but it is not unit free, as it is defined as the average of the third power of deviations from mean. Mu3 equal to expectation of x minus expectation of x whole cube. It would be expressed in the cube of the unit of x. For example, if x denotes height of a person, and if it is measured in centimeters, then mu3 is expressed in centimeter cube. If x denotes income of a person in rupees, then mu3 is expressed in rupees cube, and so on. In such cases, it is not possible to compare skewness present in two or more than two data sets because the different data sets may have different units. Suppose we have two data sets. One data set is on height of persons measured in centimeter, and the other data set is on weight of persons measured in kilogram. We are interested in knowing as to in which data set there is more skewness. Now, if we calculate the third central moment for both the data sets, then it is true that it would indicate the amount of skewness in both the data sets. But can we compare skewness in both the data sets on the basis of the values of the third central moment? How can we? The third central moment for the two data sets have different units. For the data set of height, it is in centimeter cube. And for the data set of weight, it is in kilogram cube. It is not comparable. So, for making this comparison valid, we have to find out a measure which is unit free. We define beta 1 as mu3 square by mu2q. Here mu3 has the third power of unit, and so in its numerator mu3 square has the sixth power of unit. Obviously, mu2 has the second power of unit, and so in the denominator of beta 1, mu2q has the sixth power of unit. Thus, both numerator and denominator in beta 1 have the sixth power of unit. And when we take the ratio of the two, they are cancelled out. And beta 1 thus becomes unit free. Similarly, in the numerator of beta 2, mu 4 has the fourth power of unit. And in its denominator, mu 2 square has also the fourth power of unit. And so if we take the ratio of the two, these units are cancelled out, and that makes beta 2 unit free. Now one more point, an important point I would like to discuss before I conclude. Generally, as a measure of skewness, instead of beta 1, we use gamma 1 coefficient, which is the square root of beta 1. Why? What is the logic behind it? We know that skewness in a data set may be positive or it may be negative. But we find that the value of beta 1 would always be positive, as its power in numerator and denominator is 6, which is even, and thus its value cannot be negative. So even if the third central moment is negative, that is, skewness is negative, beta 1 would be positive. So we take the square root of beta 1, which may be positive, which may be negative. We take positive sign in gamma 1 if mu 3 is positive, and negative sign if mu 3 is negative. Again, for measuring kurtosis, instead of beta 2, we generally use gamma 2 coefficient, which is defined as gamma 2 equal to beta 2 minus 3. Why so? The reason is obvious. We put kurtosis in three categories: leptokurtic, mesokurtic, which is also known as normal, and platykurtic. For mesokurtic curves, that is for normal curves, the value of beta 2 is always 3. Leptokurtic curves are those curves whose top is more peaked than that of normal curve. And platykurtic curves are those curves whose top is more flat than that of the normal curve, whose top is flatter than that of the normal curve. So The curve is leptocotic if beta 2 is greater than 3, that is, if gamma 2 is greater than 0. The curve is mesocotic, that is normal, if beta 2 is equal to 3, that is, if gamma 2 is equal to 0. And the curve is platycotic if beta 2 is less than 3, that is, gamma 2 is less than 0. About other coefficients that we generally use as measures of various characteristics of populations, I would come to you very soon. Thank you. Thank you very much.